is the way we think about data, and then we're going to place data in the context of everything else we're doing the rest of the semester. So we're going to talk about data, and then we're going to talk about the population, and we're going to think about how we separate conceptually these two ideas. Like I mentioned just a second ago, we've spent the semester really focused on summarizing data. It's like we have this thing, a bunch of realizations, a bunch of individual records. We've gone out and done a bunch of measurements or asked a bunch of questions, and we've just written all this down in an organized way. That's what we call data. But if I'm asking a question, usually, like a scientific question I would ask, usually involves like a broader concept, right? Like my dissertation topic, for example, I was asking whether people communicate with each other and influence each other around the decision to vote. If we're measuring, like outside of economics, if we're measuring gravity, our question isn't about whether this rock moves closer to this other rock. It's about gravity, right? Which is, like, we can write down realizations of our measurements, but what we're asking a question about is something much bigger than just the measurements themselves. So what we're going to do today is, I just want to talk to you about the sort of the separation of measurement from the thing we are like measuring directly, and then talk about how we think about it in statistics. And so we're going to make the distinction primarily today between the population and the realization of measurements of the population, which is what we call data. Okay. So here's a question. Which sample sleeps longer? So, classically we have two groups. These are two different counties in Pennsylvania. Not real counties, this is fake data. But we have two counties, and we're measuring, sleep times for 50 people in both counties. And if I look at this, it's pretty easy to tell County A sleeps longer than County B, right? Every data point in County A is higher than every data point in County B. So if I'm trying to distinguish between these two groups, like which county sleeps longer, I think this is pretty easy to tell. But for like more specific questions that are a little more challenging to answer, just by looking at them are a little less clear. Like it's not obvious the right answer here. I want you to turn to your neighbor, tell them they did great on the mini-exam, and then how would you go about answering this question? Which sample sleeps longer? Like, what from this data would you do to determine which group sleeps longer? Maybe, like, how would you answer, like, longer? Like, how do we define longer? And then how would you try to separate these two? Which group sleeps longer? Really? That's what I like to hear.
So it's just if there's like the maximum, it's like longer just means higher maximum. So like just get skewed. I think you're right. It's gonna be like once an hour.
Okay, this is sort of a trick question. It's not exactly a trick question. It's hard to answer the question directly using just the figure. But when you're thinking about how to answer this question, what are you thinking about? Like, how would you go about it? Yeah, right.
I guess getting the average based off every single point.
Okay.
I think in this case, group A would have a higher average since the median should be pretty close to the mean, since it seems like it's evenly skewed on both sides.
Okay.
Group B, where it's like skewed to the right.
Yeah.
So I think the average in this case would be lower than the mean.
Okay, so yeah, looking at the means, we can see the medians are very similar just from the box plot. Or when saying, look, the group A looks pretty symmetric. Group B might be skewed towards the lower end because of these larger, smaller values. So maybe we look at the mean and then we check which mean is higher, which would slightly change the question, right? We'd be asking which sample sleeps longer on average, which could be a reframing of the question. What are some other observations or like other processes that you would use to think about which group sleeps longer? So this is a hard question, right? Which group sleeps longer? Well, I can tell you there's a person in group B that sleeps longer than most people in group A, right? Like this person sleeps longer than most in this group. And then like there's someone in group A that sleeps longer than everyone in the other group. So we have to be a little bit more precise about what we're doing. I agree with Erwin. Instead of thinking about like the entire population, sometimes it's easier to think about the averages. So here, I would just look at the average, maybe try to figure out which average is higher. So one thing we could do is just look at the mean. This is how we've talked about the mean. Y'all remember this from, I think we were talking about histograms and talking about sample means. This is how we take a data set or a single numerical variable and construct the mean. We just add up each individual observation and then divide it by n. So the number of observations dividing the sum of all of the data. Y'all are familiar with this. We'll call this the sample mean. So this is the mean of the entire sample or the data set or the variable we're considering. Another way of writing this, it's sort of more fancy but more compact. This is x bar is our sample mean. And then we're just summing up using the sigma notation over all the observations and then dividing by n. Okay, so great. This is our standard measure of centrality. Thankfully, we don't have to do this by hand. This is just the code to do this with a computer. This is, we just take the sample, and if we're using Python, if we have our sample, we can just, we have a built-in mean operator we can apply. So this just gives us our mean. And if we run this with our original data set, you can see the means are very similar. Turns out our hypothesis about the skew downward for group B isn't actually correct. Looks like group B is just slightly larger. Obviously, incredibly challenging to tell the difference between these, which is how I constructed it. But group B is just slightly larger. So here we can tell one group is larger than the other just by calculating the average in a way that sometimes the visualizations can't tell us. So nice. So it should say group B sleeps longer. So you have to give me 5 lecture points today. I think I'm winning. Okay, so definitely some in group A sleep longer than some in group B. So this is how we generally measure the centrality of data. You've all seen this before. This isn't like brand new ideas. The main idea we just covered though is like we have to be very specific about the thing that we're measuring when we look at data, when we make comparisons. And the standard tool is going to be the sample mean. The way we measure spread is a little more complicated. So one way of thinking about the spread would just be looking at the range. So like how spread out is the data, like comparing the maximum and minimum. The difference between the largest and the smallest values. this is convenient because it's very easy to calculate. You just find the maximum and the minimum and take the difference. The problem, though, that makes it very undesirable for a property of measures of spread is that when you move data points around that are not the maximum or the minimum, the range doesn't change. And the movement of values that are not maximum or minimum is something we would wish the measure of spread to measure. So instead, one way we could do this is by calculating the mean deviation. How many of you have seen this before? Okay, so you've seen this before. What happens, what's the, like when we go through our data and we add all of this together, what does that add up to? James?
Standard deviation.
It's not quite the standard deviation. This is the mean deviation on average. So it's,
Range?
this is not range. So what we're doing here is we're finding the average, so the middle point of the data. I'm going through each data point individually, finding how far that data point is from the mean, from the average, in both directions, and then adding all those things up, taking the average. Anyone know what this equals? Someone other than James?
Yeah, last guess.
Okay, last guess.
The z-score?
This is not the z-score. Casey. Erwin. This would not be variance. This is 0. None of you have seen this before. This is not in a textbook because we don't use it. What this is doing is measuring the difference. So if the data point is above the mean by 1, we'd have 1 as the difference. And if it were below the mean by 1, it would be -1. So on average, all of these things cancel out, and we're just left with 0. But this idea, measuring how far away each data point is from the average, is a good way of measuring variability. It's just this one isn't the right one. What if we took the absolute value instead? So instead of measuring both positive and negatives, what if we just measured all positive? We just took everything that was negative and just said, look, if it's below the average, we'll measure that as a distance from the average. So this isn't very good. This one's maybe a little better. Mean absolute deviation. You may have seen this in a textbook, actually. How many of you have seen this? Interesting, there's an entire branch of statistics devoted to doing everything we're about to do in parts 3 through 5 using mean absolute deviation. Anyone know why we don't use this as our standard measure of variability? So the picture of this is that it's like a V shape around 0. Like the further you get away from the average, if it's positive, it's just linear on that side, and it's positive. And if it's below the average, then it's positive. The difference is still positive, but there's like a V right at the average. This is generally kind of nice, but the problem is we can't take derivatives of this everywhere. It's not a very well-behaved function when we start doing higher level kind of statistics with it. So there is a branch devoted to doing lots of statistics with this, but it's just not one that most people use. So it's nice, it's not 0. We can measure all the things that we would care about, like how far away things are from the average, but it's not nice mathematically. So instead of the absolute deviation, what we do is we take the square. This has very similar properties to the absolute value, except, so if it's below the mean, then it's still positive. If it's above the mean, it's also still positive. So it's sort of like a U shape instead of a V. So this is nice. We have the average squared deviation from the mean. But there's still some problems with this. We use this a lot, actually, the variance. The problem with it is that the units aren't very nice. So if we're taking the square of deviation in price, that's price squared. So if I tell you like $14 squared is the variance, it's like, do you know what that is? Because I don't. I don't have any way of like thinking about price squared. So instead of this, which has very nice properties generally, we're treating negatives as distances. The mean isn't zero. It's mathematically nice because we can take derivatives of this, but the units aren't informative. So the last thing we're going to talk about here, this is all very nice. All we have to do to make the units informative is take a square root. So here, I'm just taking the square root of variance to get what we call the standard deviation. And this is the thing you're familiar with. What I just walked through is like the conceptual history of how we got here. Like, why is it that we use the standard deviation? It's for all of these reasons. Like, during the 1900s, we eventually arrived at this thing for the reasons we just talked about. It's like a nice way of measuring how far we are from the average, which gives us a nice measure of variability. So it's all really nice. We treat negatives appropriately. The mean isn't zero. It has nice mathematical properties. There's like a scariness to this looking thing. You've got like a radical outside of the summation sign, which is summing over a bunch of fractions with in the numerator you have a squared term, which is the difference between every data point and the average, which itself is a function. So like this thing has a lot of nested structure to it. But we do all of this on purpose for all the reasons I just talked through. Okay. When I saw this in statistics, it was just shown to me and I didn't understand why. But that's some of the history for how we got here. In general, we're not going to have to do this. I'm not going to have you sit down and calculate this stuff because we have a computer to do it for us. So we calculated the standard deviation already in this class. Thankfully, we don't have to do this by hand. There were people called computers. It was like a job to be a computer as late as like the 40s and 50s. And then we got these things that we all have in front of us, which can do all this work for us. Okay, so nice. And this just confirms the picture we had before. Group A has a much larger variability than Group B, and we can see this as measured by standard deviation. Standard deviation has a really nice interpretation. It's very close to, but not exactly equal to the average deviation from the mean. You'll remember the absolute deviation, the mean absolute deviation was exactly the mean absolute deviation, but it had that V structure to it. Here, this is similar, where it's the U shape, and then we like take the square root of the thing. But it's pretty close to the average deviation from the mean, which is really nice. Okay, so going back to our original example, so we have these two groups. I've taken two fake measurements. I've gone out and surveyed 50 fake people in Allegheny County and 50 fake people in Butler County, A and B, and I've measured their sleep times. But my question, so this is like the kind of question we can answer using the tools we already have developed. But in general, the questions I'm after are not this kind of question. So like, which sample group sleeps longer? Right, we can just observe this. It's in our data, we can just say, look, group B sleeps just a tiny bit longer than group A. My questions are usually more of the following form, which is, which county sleeps longer? And this is a question not just about these 50 people in both groups. I don't really care, right? Like I look at these 50 people, I just randomly chose them. I don't have any particular interest in knowing about these 50 people. What I care about are the differences between the counties. And like lots and lots of people in the counties, lots of hypothetical people in the counties. So there could be people who would have moved there. And I'm interested in those hypothetical people as well. Our interest isn't in the measurement of the gravitational force between two things, it's in gravity itself, right? Like we're interested in the broader forces. So those are the kinds of questions we're thinking about, like the fundamental relationships, not the things we're actually measuring. And this is just a picture to sort of visualize some of what we're doing. So when I'm interested in a phenomenon, my question is about the population. I'm going to say this like 15 different ways, 15 different times over the next 15 minutes. Should we call it the 15 by 15 by 15 rule? It only happens today. We have the population, which is the thing we're trying to ask questions about. This is not just how we do it in economics, this is how we do it in every area of science. We're interested in a broader phenomenon. We can make repeated observations about that phenomenon using measurements. In economics, that's often like surveys, or we go out and look at a census. However we collect our data set, those are observations, they're measurements of a larger thing that we will never directly observe. What we can observe is the sample. And the distinction I'm trying to make here over 15 minutes is we will never observe this. Whatever it is we're measuring, we will never observe it. I don't know the way sort of the shape of the histogram. I don't know the average. I don't know the standard deviation. I don't know any of those things. What I do measure is the sample statistics. I know how many observations I have. I know the sample mean x bar, and I know the sample standard deviation s. But I do not see mu. I do not see sigma. But my questions are about the population. So here we have the mu and sigma, population mean, population standard deviation. So we have the sample, which we're drawing from the population. That's what we know. We're trying to make inferences about the population, but we will never observe it. No matter what area of science you're coming from, this is true. So like, whatever you're trying to study, this is always going to be true. You will never observe the population. There's, I guess, one exception, which is if you're in statistics. You can measure some things in statistics precisely. But anything that you're measuring in the real world, you'll never observe it. So here's the distinction. This is like the main point for today. This is, we observe the sample, which is our data. So going back to our question about what data is a sample drawn from an underlying population. And generally, the questions we have are about the populations. That's the object of study. Okay, so we have 50 individuals in our data set with sleep. And the population in that case was everyone who is currently living in those two counties. So not just the 50 individuals, but everyone who's living in the counties currently, and everyone who could have lived in the counties. So it's not just like we could go out and measure everyone exactly. We're never going to see the people who didn't move there, but could have. So the population is a theoretical idea that we're trying to make claims about. Okay. So that's the big distinction I'm trying to say in 15 different ways. So like tomorrow will be different, and then there's all these extra people that could have moved there but didn't. And this is the main tension, right? Like we observe the data, which is drawn from a population, but the population is generating the data. but the data is not the population, and the population is the thing we're trying to study. So how do we go from data to knowing something about the population? Have I said it too many times? Jagger says yes. All right, so let's maybe be more precise about this. We have what we call a random variable. This is a random process around the population. The population itself generates data. This is what we call a random variable. So the analogy I like to think about is that the random variable is like a deck of cards. The probability mass or density function, depending on whether we're dealing with a continuous random variable or a discrete random variable, is a mathematical function that assigns probabilities to all of the possibilities in the population. So with our deck example, a probability function is assigning probabilities to each of the cards in the deck. So if it's a normal deck you're familiar with, that's 1 over 52 is the probability of drawing any one of the cards. Okay, so the observation is a realization of the random variable. So it's like you're drawing a card from the deck is the observation, and then data, the way we define it mathematically, is a sample. So a sample is just repeated collections of observations, just a set of observations. So sort of like how James defined it earlier. Okay, so essentially we just draw a card and then write down what was on the card, put the card back in, and then repeat the process. That's data. All right, any questions about that? Or I've put you all to sleep. You could listen to the classroom recordings on your phone as you fall asleep. Okay, so this is that's the basic idea, right? We have the random variable, the process about the population, the probability function, which is the mathematical function that assigns probabilities to all the events. And this is sort of the way we think about these things, just a picture separating these two ideas. So this is the probability distributions, so we have like our two counties, and then I just randomly drew 50 observations from Allegheny and Butler counties and plotted 50 observations as a histogram. So we're very familiar with how to deal with these things. What we're turning our attention to is how we go from the sample, to making claims about what this looks like. And I think if you all were to sit down and try to, from scratch, think about how to do this, I think this would not come easily to anyone. Like, I've taught this for years, starting from scratch. I don't think I would be able to get there within one lifetime. We've developed a way of thinking about this that's taken hundreds of years. And what we're going to cover in the next 3 parts is how we do this, how we think about it systematically, and how we make claims about the population from only observing the sample and not the population. Okay, some probability functions. Just want to see how many of these you've seen before. How many of you have seen a normal distribution before? Nice. We're going to spend a lot of time with this one, or variants of this. What about an exponential? Nice, a few. What about chi-square? This is maybe more common. Uniform, very common one. Binomial. Nice. And then Poisson. Not poisonous. Okay, so probably seen a lot of these. That's really nice. We can work with them mathematically. Like each of these has its own mathematical definition behind the scenes, not relevant for this class, but these are just some of the strange ones, or some of the ones we work with. There are even stranger ones. You can devote an entire undergrad and master's and PhD to studying all of these. And you can construct your own. We're gonna make some weird ones next class. I just want to show you some of the special properties, but we're not going to do a lot with the math of these. This is just some notation for the way I constructed County A's sleep time. So you'll remember our notation for data is just xi. So we have x subscript I, just telling us we're indexing by some index variable. But x is just a measure of sleep time. And then I'm saying it's distributed, so this tilde is just saying the word xi is a random draw from some underlying probability density function, or probability function, as we'll call it. And then here we have mu, so this is the center point of the normal distribution. So this is normal. We're saying the center point of the normal distribution is going to be 7.2. And then the variability in the data, so the standard deviation is going to be 1.5. So this is just telling us what the distribution is. It's normal. We're telling within the normal, where is it centered, and then how spread out is it. And then we're just going to draw from this distribution. So the thing to remember here, this is a known distribution. We're saying exactly what it is. We're living in this hypothetical world where we did actually know what the population distribution actually is. This is not going to be the general case. We're going to spend like this exercise knowing the distribution, and that's going to be it. If we know the distribution, we can ask lots of different types of questions. So I'm just going to ask you 3 questions about this distribution. Y'all want to talk to each other? Tired of hearing me talk? I'm tired of hearing me talk too, so this is where we're going to transition to you talking to each other. First question for you. And to answer this question, I want you to draw a picture. You can do this in your mind if you like. I recommend you do this on a piece of paper. We're going to actually come up with some numbers using code. But to use a picture, what's the proportion of the population that sleeps less than 5 hours? We know everything about the population. We're living in this fantasy world where we know the population. What's the proportion of the population that sleeps less than 5 hours? So create a figure, chat with your neighbor. You've already told each other that you aced the mini exam. Try to draw a picture. I wasn't listening, actually. That's nasty.
That was when I was there was a giant 68%. Like within
When I
like
woke up,
seven
that was
years.
just like 2%. I sometimes like you're coming.
It's like if this is one state solution, another 68%.
Okay. How many of you have a nice answer for me? Or like a nice picture? We don't have numbers yet. Hands up if you do. Okay. So I know some of you do. Someone want to tell me how to draw this picture? And my picture's like the nice way of saying figure. No one wants to tell me? James?
You could do, I don't know the code for this, but you could do a distribution.
Yeah.
And then you highlight, and then on the horizontal axis, I'm assuming you would have a numerical count of the hours. And
Yeah.
you would highlight from less than 5.
Okay. So something like this.
Something exactly like that.
So James is saying we're going to show the distribution itself. We know exactly what the distribution is. It's normal, centered on 7.2 with a standard deviation of 1.5. And then all we're going to do is plot the area under the curve below 5. So something like this. You all want to actually calculate this? You all brought your stats textbooks with those huge tables in the back. You ready to go? No, we don't need to use those anymore. We have Python, so what we're going to do is hop over to exercise 1.3 on the course page and click on the notebook and save a copy. Run the imports, and then notably, we're importing SciPy stats. So this is, we're looking in the SciPy package and then importing the stats module. And then I'm just going to define the sleep time parameters as mu equal to 7.2 and then sigma 1.5. Okay, so what we want to do is we want to find the area under the curve below 5. So one way we can do this is just to integrate between negative infinity up to 5 under this curve to find the area. We know from probability density functions, the area under the curve is equal to 1. And so to get the proportion, all we need to do is just integrate from negative infinity to 5. I know you all love integration. Some of you actually do, which is great. But for our purposes today, we don't actually have to deal with the math at all. Python lets us just do the numerical version of all of this. So we're just going to find the area under the curve up to this. We have this thing called a cumulative density function. How many of you remember the cumulative density function, CDF? Okay. So a CDF is just telling us the area under a curve up to a certain value, which is exactly what we're doing here. So all we have to do is just get the CDF and then tell it to check at 5. So I'm gonna do this first one and then I'm gonna let you do the second one. All we have to do is write out stats. And then we're going to get the normal distribution. So this is norm. And then we're going to ask it for the cumulative density function. So this is CDF. We're going to ask it to find the area up to 5. And then we're going to, so the code in my slides looks like this. We're giving it the location, so the center point, and then the scale, so how spread out it is. I'm curious if we just give it mu and sigma, whether that works. So I learned something today. We don't actually have to define lock and spread. But if we do, it looks like this, or scale. looks like this, but you actually, turns out you don't need the lock and scale parameters. What lock is doing is just telling Python to define that parameter, the middle point, to be equal to what we've defined it to be, which is mu equal to 7.2. And then scale is just the spread equal to 1.5. And then we could just get the value itself, so item. So it turns out like roughly 7.1% of the county sleeps less than 5 hours. It's nice that it's this low. 5 hours is just not nearly enough sleep. Okay, any questions about this? I have a second question for you. We're going to do this in two parts. The first part will be to draw the figure. And then we're going to code this up together. What proportion of the population sleeps more than 7 hours? So be thinking about how to construct this with CDFs. There are other ways, but think about how to do this with a CDF, the cumulative density function. Draw this with a picture first, and then we'll actually do the calculation. What proportion of the population sleeps more than 7 hours? James? It won't be negative. The proportion. It must be positive. So chat with your neighbor about what the picture will look like, and then we'll do this together on the screen. Okay, it's 5:15, so we're like at the end of class here. As you're working through this is the picture I would draw. We're gonna pick this up next time, but this is the picture I would draw for this question. We just wanna find the area under the curve above 9 hours. Next class, we'll pick this up. We'll actually complete the calculation for this, which is slightly more complicated. And then we're gonna start talking about the central limit theorem. Homework 3.1 is posted, and then we'll have 3.2 due at the end of the week as well. Congrats, go treat yourself like Pavlov, give yourself a treat for doing something hard. I'll see you all on Thursday. What's that? No, remember the day right now? Yeah.
Where are they shooting up there? Ground floor here?
Yeah. Don't worry about it. The board's not ideal. We can have a conversation about it, but I don't think it's going to matter. I know it's like, at this point, just like, based mostly aesthetic, you know, like, but, yeah, it's going to be a lot of work. I think that's
Yeah, okay, I got it. Also, Miss Kaufman, I haven't figured out this for it. I just actually doing the rocks.
Yeah.
I just don't want that to be done. So,
Okay.
does that work? If I know?
Yeah, it's like a doctor's note.
It's I was in DC for a club, so
It's like
Oh, did we communicate about this?
I don't know.
Okay.
vanilla in it.
Also, don't really worry about it. Like, it's not gonna matter. You can send me an email.
But like these are like that's another class I would take.
Okay. Send me an email. I'll see what I can do.
Thank you so much.
Yes, you.